Flameproof XD systems assume an internal explosion will occur and use heavy steel enclosures to contain the force. Intrinsic safety, or XI, works by stripping away the energy source before a spark can even form. Because there are no thick metal walls to rely on, intrinsic safety operates on mathematical verification. Before hardware is installed in the field, an engineer must prove that a thermal discharge with enough energy to ignite surrounding gas is physically impossible. This verification relies on an intrinsic safety barrier that clamps voltage and current to specific limits. This is the IEC 79-11 ignition curve for resistive circuits, plotting the exact thresholds to ignite hazardous gases. The area below represents safe operation. As long as the barrier restricts values to this lower zone, the system cannot generate an incendiary spark. If values cross above, the circuit becomes a hazard. The required margin between operating parameters and that threshold is determined by the fault tolerance category. Category IA requires a large safety buffer, remaining safe with 2 independent faults, while IC is evaluated only for normal operation. Effectively, an XI system is a strict energy budget. The barrier dictates the absolute maximum allowable power for the entire loop, and every component connected to it must fit within that specific allocation. This strict energy accounting allows for a unique regulatory exemption for a class of equipment known as the simple apparatus. To qualify as a simple apparatus, a device must be physically incapable of generating or storing significant energy. IEC standards define this threshold precisely. The component cannot exceed 1.5 volts, 100 milliamps, and 25 milliwatts. Passive field devices like thermocouples and RTDs meet these criteria. Operating within these limits, they lack the physics required to yield an incendiary spark. They cannot draw enough energy to cross the gas ignition thresholds. Because they are limited by their own internal physics, regulatory bodies do not require a simple apparatus to carry a formal X certification or an engraved ATEX marking plate. There is a critical condition to this rule. This exemption only applies if the simple apparatus is wired to a certified intrinsic safety barrier that guarantees those maximum energy limits are never breached from the supply side. This exemption reduces equipment costs, but it places the regulatory burden of proof on the designer. You must mathematically verify the safety of the entire loop using the barrier's data. Without a pre-certified system certificate covering your specific combination of devices, you must verify 5 mathematical inequalities defined in IEC 60079-14 to prove the loop is safe. We start by mapping the output side of the loop. Under fault conditions, the IS barrier will permit a maximum output voltage, labeled UO, a maximum short circuit current, IO, and a maximum output power, PO. The first inequality matches voltage. The field device's maximum safe input voltage, UI, must be greater than or equal to the barrier's maximum output voltage, UO. The instrument must withstand the barrier's worst-case voltage spike without failing dangerously. Next is the current match. The device's maximum input current, II, must be greater than or equal to the barrier's maximum output current, IO, ensuring it can safely handle a dead short. The third check is power. The maximum input power rating of the device, PI, must exceed the barrier's maximum fault power output, PO. Passing these 3 power inequalities confirms the 2 devices are compatible. However, this calculation only proves they are safe if connected directly together. It does not account for the wiring between them. The most frequent error in loop design is viewing the field cable as a simple conduit for signals. In an intrinsically safe circuit, the cable acts as a distributed capacitor and inductor, actively storing energy as current flows through it. The capacitance and inductance of that cable increase at a linear rate for every meter it extends into the hazardous area. A transmitter and barrier combination, verified safe for a 50-meter run, can become a lethal ignition hazard if the installation is extended to 400 meters. The added length stores enough energy to produce an incendiary spark if the cable is damaged. Even with ATEX-certified barriers and transmitters, a loop can cause an explosion if the energy storage of the cable is ignored during the design phase. To account for this, The barrier carries strict storage limits, a maximum external capacitance, CO, and a maximum external inductance, LO. The fourth inequality calculates capacitance. The total capacitance of the cable plus any internal capacitance of the field device, CI, must not exceed the barrier's maximum allowance, CO. The fifth inequality calculates inductance. The total cable inductance plus the device's internal inductance, Li, must remain below the barrier's limit, Lo. When the cable length surpasses the barrier's allowance, the combined stored energy breaches the CO or LO thresholds. The mathematical proof fails, and the loop is no longer safe to energize. This creates a strict engineering requirement. Verification calculations must always use the as-built cable length from the field installation, not a generic estimate from datasheets. Verifying this storage budget is what translates a theoretical paper design into a physically safe installation. While the 5 electrical inequalities prevent sparks, simple apparatus components introduce one final variable. Because they lack formal X certification, they also lack a predetermined temperature rating, or T-code. To prevent the component from becoming an ignition source, engineers must calculate the worst-case surface temperature of the device under fault conditions. This requires a specific thermal formula. The barrier's maximum power output, PO, is multiplied by the device's thermal resistance, RTH, and then added to the maximum ambient temperature of the environment, T ambient. This resulting value is your maximum potential surface temperature. This number must remain below the auto-ignition temperature of the specific explosive gas present in that zone. This thermal check closes the final loophole. It ensures the device cannot cause an ignition through radiant heat, even if electrical sparks are successfully suppressed. Consider a scenario where a loop passes the UI, II, and PI checks. With a 500-meter cable run, what is missing from this verification? Matching the voltage, current, and power is insufficient if you have not verified the CO and LO storage limits for that 500-meter cable run. Think of a long electrical cable storing energy like a massive industrial hose holding water under pressure. The physical length dictates the system's energy capacity. This checklist summarizes the completed IEC 60079-14 mathematical framework. These 5 integrated environments without compromising facility safety. Intrinsic safety relies on keeping power levels low. But when heavy switchgear and large motors require massive amounts of energy, we must move beyond energy limitation and look at the mechanics of pressurization, or XP.